Today we'll be beginning with chapter 5 of the syllabus and the text. Well, actually, if you look at the 2026 syllabus and onwards, I believe it's published till 2028. They've actually changed the numbering a bit, so it's not quite as what you'd find in the textbook. The chapter numbers in the textbook were aligned to the syllabus for 2023 to 2025. So according to that, this is chapter 5. And it is termed electrochemistry. Right, and so as the name suggests, we will be talking about how electricity, is put to use in chemistry. And what we'll basically be talking about is a process called electrolysis. So by definition, electrolysis is the decomposition or in simpler terms, the breakdown of an ionic compound. Right? Ionic compound when it is either in its molten or aqueous state, by the passage of an electric current. Right? And then whatever ionic compound is being used either in the molten or aqueous state, in this case, in the process of electrolysis, it is termed as an electrolyte. Right? So an electrolyte is the ionic compound being used in electrolysis. Right? Again, either in its molten, right, or aqueous, as an aqueous solution. And right, the electric current is passed through the electrolyte using electrodes. Right, so the electrodes are, right, either made of unreactive metal, such as platinum, or made of non-metal, and right, to be specific, carbon, and to be more specific, graphite. So right, either of these two are usually used to form electrodes, and right? The reason being that they are inert. So this either unreactive or it's carbon, which in most cases, right, we'll see that in some cases the carbon, does end up being depleted, and the reason why, but for the most part, right, they are inert. Inert means that they do not, uh, you know, react themselves. So they do not react with the products of the electrolysis. All right, so we've come across the term inert earlier, I believe, when we talked about the noble gases uh, in the periodic table, the group 8 elements, and right, so they're inert, so they don't react at all, right? Some artificial compounds have been made using them, but on their own they do not undergo any reaction, so they're inert, right? Similarly, uh, right, another example of something that's inert is the nitrogen gas that is filled in, for example, packets of chips. So they're all blown up, and that's because there's nitrogen gas in them, so that they do not become soggy, don't react with moisture. So there shouldn't be moisture in the packing, there shouldn't be oxygen, because that's going to react as well. And so when you open a packet of chips, right, all that nitrogen is released, and so you can still eat them crisp in most cases, right? So nitrogen on its own as a diatomic gas, right, in its elemental state, is also inert, right? But of course, in case of nitrogen, it can undergo reactions. So inert basically means that it's not reacting. All right, what else? Now the electrodes, right, are connected to a supply of electricity. And in this case, right, we know that there's positive and negative charge. And so the electrode which is connected to, uh, the positive terminal. So positive electrode basically mean it's connected to the positive terminal of, the electric supply, is called the anode. And we also know that opposites attract, right? So positive and negative will attract. So if this is the positive electrode, it's going to attract the negatively charged ions, right? Because we're talking about ionic compounds. And because these negatively charged ions move towards the anode, they are called anions. So anions are negatively charged ions. So not to confuse, right? Anions are negatively charged. They move towards the anode. Because they're moving, that means they're being attracted. That means the anode has the opposite charge, and the opposite to negative is positive, obviously. Right?
Can
Yeah.
you explain what is electrolysis?
Electrolysis.
Oh yeah.
It is like so, right? We'll look at examples, and so what's happening is that they take an ionic compound, either in its molten state, so you take a solid ionic compound and you heat it to melt it, so that's molten, or you dissolve it in water, so that's aqueous solution, and then you pass electricity through it, and that causes the ionic compound to break down, so it's separate, And so you're able to separate the metal and the non-metal, because we know from chapter 3, which is bonding and structure, that ionic compounds are formed due to a reaction between metals and non-metals. And so you're able to break that down and separate the metallic ions and the non-metallic ions. And then in that case, you're able to separate the element itself. Okay.
Yeah.
So everything else I mentioned about what an electrolyte is and the electrodes and all of that, is that clear?
Yeah.
Okay. So again, right, the electrodes are connected to a supply of electricity. The positive electrode is called the anode and attracts the negatively charged ions. And in that case, those are called anions. And the negative electrode is called the cathode, and it attracts the positively charged ions. And because the positively charged ions are moving towards the cathode, they are called cations. Right? So they have a positive charge. Right. So you have the positive charge ions, right? Cations moving towards the cathode. What else? Now, right, they go on to talk about how electrolysis works and all of that. I'm going to actually skip ahead and talk about what you would normally expect to happen during the process of electrolysis. Right, and then we look at examples by which that would become clearer. So this is something that's actually mentioned later on in the chapter, and that is electrolysis guidelines. So because we are dealing with ionic compounds, right, which is basically in most cases, right, metal plus non-metal. And we remember from ionic bonding that metals lose electrons, so they form, right? So metals are the cations, and then the non-metals are the negatively charged ones, because they're gaining electrons, are the anions. There's another cation that comes into the mix, which is hydrogen. Right? And so keeping that in mind, there are a few things to consider when electrolysis is happening. So the anode is positively charged. It is attracting the negatively charged ions, which are the anions. And so, right, non-metals are produced at the anode. Are produced, why? Because again, electrolysis is breaking down the ionic compound. It's separating the ions, right? It's breaking the ionic bonding, right? And this is actually a difficult process, because you have to supply electricity, you have to use a molten or aqueous solution of that thing, right? And you have to pass electricity through it, and right, so ionic bonding is actually very, very strong, right? And so, right, you end up, when you separate them, the non-metals, the non-metals, the anions, they are produced at the anode, right? And either hydrogen gas or metals, or and metals, are produced at the cathode. So that's one thing to keep in mind. Then at an inert anode, so one that's not reacting, what you would expect is the halogens are produced in preference to oxygen. And this will make sense when we look at the examples of the kind of electrolysis reactions, uh, right, processes that can take place. So chlorine, bromine, and iodine, which are the halogens, group 7, are produced in preference to oxygen. And then thirdly, so this is about the anode. At an inert cathode, so this guy is bringing in the positive ions. It's negatively charged itself. Hydrogen is produced in preference to metals. So we talked about hydrogen gas and or metals being produced, but right, hydrogen is produced in preference to metals. So if both cations are present, both hydrogen and a metal cation, hydrogen will be preferred unless the metal is unreactive. Unreactive metals such as copper are used, are present, in fact. Right? So we've talked about metals, we've talked about the reactivity series, and so copper is way down in the reactivity series. It's not very reactive. And so it's not completely unreactive, but it is quite unreactive. Right? But if you've got more reactive metals such as aluminium or right, sodium, for example, or magnesium, then right, instead of those, hydrogen will be produced at the cathode. If you've got the unreactive metals, then right, you will have, and that is in case hydrogen is present in right, whatever substance, whatever electrolyte we are using, or somewhere in the process of electrolysis. If there is no hydrogen present at all, then obviously then the metal itself will be coming in. Is that clear?
Yeah.
Okay, now this is all theoretical. We haven't seen any electrolysis happening yet, right? So these are just guidelines and things to keep in mind, and definitions. So let's take a look at an example of electrolysis. So right, uh, oh, another thing, sorry. If I just go back, substances, in fact, let's go forward. Substances that conduct electricity to a small extent when they are, either in the molten state or in solution. So they are called weak electrolytes because they're not doing a very good job. And then, right, substances that do not conduct electricity. When in their molten state or aqueous solution, they are called non-electrolytes. Right. And right, the reason that electrolytes are able to conduct electricity, right, because again, when they are molten or in solution, the ions are free to move. Right, and the ions are charged, so they're charged particles, and electricity is a flow of charge, right? So when the ions are moving to the electrodes, right, they cause a flow of, they carry the electricity. And again, right, why are the ions free to move? Because when in molten or aqueous solution, right, the forces, the electrostatic force of attraction between them is weakened. So the electrostatic forces of attraction between the ions, right, are weakened. Okay. So for an illustration, I'll take you to the book. Let me just put that on screen. Okay. Can you see that? Can you see the text?
Yeah.
Okay, so this is a setup. And what you have over here is this is a power supply. This is a bulb, right? Why is that? We'll see. And right, this is an inert carbon cathode, so it's negatively charged. And that means it will be attracting the cations, which are positively charged. And this is an inert carbon anode, so it's positively charged, and so it will be attracting the anions, which are negatively charged. And this is the electrolyte. Right, so this is a general setup. What you would, right? Now, obviously, specific setups can be different, but just for a general understanding. So they talk about an experiment over here using lead to bromide, right? So PbBr2 over here, sorry, over here, right? Lead to bromide. And so they're using that in its molten state. So you've got the setup over here again, the cathode and the anode, right? And you see, the symbols are important. So you see how this is made, the power supply, the short thin line is the cathode, that's the negative terminal, right? The thick longer line is the anode, that's the positive terminal. and then you've got solid lead to bromide, and so they heat it to turn it molten. And so, right, in its solid state, there's no electricity passing through, right? So in a circuit, electricity needs to pass through somewhere, right? It needs to go somewhere. And so nothing's happening over here. In the molten state, electricity is able to, because lead to bromide is ionic, right? You've got lead, which is a metal, and bromine, a halogen, right? Which is a non-metal. So it's a classic example, such as, right, potassium iodide or sodium chloride or magnesium chloride or any of those other, right, halogen compounds. So right now it's not very clear. If I just zoom in, right, you can see that these yellow lines on the illustration for the bulb means the bulb is lighting up, right? The bulb is lighting up. Why? Because electricity is flowing, right? It's passing through the entire setup. So now, right, the bulb is lighting up. So that's an indication of electrolysis is working. And then what you would notice in case of lead to bromide, so, right, uh, if you go to the whiteboard, lead to bromide, right, is Pb, that's lead, and sorry, Br2. And so what you have over here are basically the lead ions, which are Pb2 plus, and the bromide ions, which are Br minus, right? And if you want to balance that, that's how it looks like, right? So you've got one atom of lead combining with two atoms of bromine. And so these ions are separated. And because these are positive, they're going to move to the cathode. And these are negative, so they're going to move to the anode. And so these are anions and these are cations. And so what you will notice at the cathode is lead, molten lead will start to deposit. Why molten lead? Because you are using molten lead bromide, right? So molten lead collects at the cathode, and right, bromine gas, right, bromine vapor is seen at the anode. Okay. Uh, yeah. Any questions?
No.
So overall, what, right? So you can take a look at what's happening to the ions individually, and right, what's happening is the first of all, right, overall, in fact, here's the whiteboard. Okay, you have Pb Br2 being converted into bromine gas, Br2 gas, and lead, which is, right, a liquid. So it's in molten state, and this guy is also in molten state. Individually, if you take a look at it, if you take a look at the ions, what's happening is, right, you've got the lead ions, and this means that lead has lost two electrons. So it moves to the cathode and it gains two electrons. And so it becomes, right, just lead, right, in its a lead atom. And what's happening at the anode, so bromine is, right, losing electrons, because the minus means that it has an extra electron more than it normally has in its uh, elemental atomic state. And so in this case it's going to go like this. It's going to give up that electron at the anode. So this is the cathode, this is the anode, right? And from there, these two bromines are going to, right, two of the bromine atoms are going to combine. So you're going to have two individual bromine atoms to form the diatomic bromine molecule, right? And that is going to show up as vapor in it, like bromine gas, bromine vapor. So this is a bromine. These are bromine atoms, and this is a bromine molecule. Remember that molecules are when more than one atom join together, right? And because you've got two atoms of bromine joining together, this is right, and it's just the same atoms of the same element, and so this is a diatomic molecule of the same element, right? It's a bromine molecule. Any questions?
No.
Okay. So, okay, am I missing anything? Right now, right, lead to bromide is an example of a binary compound. So PbBr2 is an example of a binary compound. Right? What's a binary compound? If you're familiar with the term binary, it means that it contains two elements that are chemically combined. Why is there a focus on two? Why is it binary? Because you can have compounds that have more than two elements. For example, you have sulfuric acid, right, which is H2SO4. So you've got three elements combined. So it's not binary, right? It's, I mean, whatever term they use for it, if there is a term, right? So just to clarify, the reason why they're stressing this is because there are other compounds that have more than two elements coming together. And so we're just talking about the ones where there are only two elements, not number of atoms. Keep that in mind, right? Only two elements that are chemically combining, even though the number of atoms is more. So you can even have, for example, aluminium chloride, and so you got four atoms, but the number of elements over here is just two. Okay.
Yeah.
All right. What else? So, right, what we learn over here in this example, that right, there is a transfer of charge during electrolysis. So in right, the example of lead to bromide, there's a transfer of charge, right? So the anion is losing its electrons, the cation is gaining electrons, and due to that flow of electrons through the circuit, right, and the molten lead bromide in this case, you see the bulb lighting up because electricity is flowing. And so the transfer of charge during electrolysis in general, right, in general is due to, so, right, something to keep in mind. The first thing is the movement of electrons in the metallic or the graphite electrodes. Okay, then the loss or gain of electrons from the external circuit at the electrodes. What does that mean? The loss or gain of electrons from the external circuit at the electrodes. What does that mean? So I'll take you back to the illustration. Just change screens. And so, right, this is your setup. You have the power supply. So this is the external circuit. And right, this is the cathode, this is the anode. And so, right, the loss of electrons. So at the cathode, the circuit is losing electrons to lead, right? Because lead is gaining 2 electrons, as we saw, to go from the lead ion to the lead atom. And then at the anode, you've got bromine coming in, which is the anion. It has extra electrons, and so the electron is being given up, right? So that electron that is being lost by bromine is being taken up at the anode. So that is the gain of electrons, right, at the anode, at the electrode, to the external circuit. And so, right, uh, you have electricity flowing through the the setup. Okay, and then the last point is that the movement of ions in the electrolyte, right? So obviously that is the key player. The movement of ions in the electrolyte. Right? And so how is electricity passing, through the electrodes? That is because if it's a metal or even if it's graphite, right? And the reason why we're using graphite, if you recall when we talked about bonding and structure, graphite has a structure of C3, right? And carbon is able to make 4 bonds. In graphite, it's only making 3 bonds. And right, so it has an extra electron to go about. So right at the electrodes, those electrodes have delocalized electrons and they are moving. So the electrodes, and if it's a metal, then that goes without saying, because the whole thing about metallic bonding is having a sea of delocalized electrons and a sea of metal atoms, or right. So the electrodes have delocalized electrons which help conduct the electricity, and right, the electrolyte has ions which we already talked about, and that is why there is a flow of electricity. Right now, electrolysis is used commercially to, for example, extract metals such as aluminium from its ore. So when we talked about metals, we talked about the fact that many elements, especially the very reactive ones, and aluminium is like third or fourth on the list. So right, the very reactive ones are found in a compound state, uh, usually oxides, and right, so those are ionic compounds and they cannot be separated easily, so they need to be separated via electrolysis. So electrolysis is something that is used to you know separate and extract aluminium from its ore. So we'll talk about that tomorrow, because right, it's just about out of time, and then we'll continue forward and talk about electrolysis and aqueous solutions, and then whatever else is left. Do you have any questions about anything we've discussed today?
No.
You sure? All clear?
Yeah.
Okay, that's good to know. So I will see you again tomorrow then, inshallah. All right.
Yeah. Allah.